Well, good morning or good afternoon or good evening to everyone, depending on where you are. I see it as 7 o'clock Eastern time here in the US, and just about time to start our panel. Uh, Obviously missing a couple of our speakers and my illustrious co-conveners. We might give folks another minute or so to arrive. Otherwise, Joanna and I think we're going to have an interesting conversation to share with you about permafrost processes and climate change. And we'll have plenty of time for discussion. So let's just give folks another minute or two, and barring any late arrivals, we'll get going. I guess I am not one to stand on ceremony or particular timing with a small group like this, but welcome to our session on permafrost processes in Antarctica and climate change. I'm Joe Levy at Colgate University, and we have a couple of good speakers here lined up today. A couple seem to have either missed out on dates or times. There seems to be some confusion, and I know it's always hard to get together, particularly in August. But I guess I'd like to start. Joanna Baptista, if you're here, I do want to turn on your camera and go first, or get your slides queued up. Awesome. Hello, and good to see you.
Hello.
So yeah, would you like to lead us off for our first talk?
Yeah.
Perfect.
I can start my presentation.
That'd be great. Go for it. So
Okay.
we have Joanna Baptista here to talk about spring snowmelt, timing controls, ground surface temperature regimes in maritime Antarctica. So certainly take it away.
So you can see the presentation. It's okay?
Looks good.
Okay. Just let me move. Okay. So hello, I will present the results obtained from the work developed on my master thesis in physical geography at the University of Lisbon. In this work, I have studied the permafrost and the ground surface temperatures recorded between March 2019 and February 2020 on Barton Peninsula, King George Island. This study was the starting point for my PhD research project. So starting with my motivation, the ground surface temperature is the key indicator of climate change in permafrost regions. In Antarctica, the permafrost is present in different environments where the topoclimatic factors show a complex impact on the ground surface temperature. The work developed aims to assess the influence of topoclimatic factors such as the elevation, the aspect, curvature, solar radiation, the topographic position, moisture, and snow cover duration on the ground surface temperature. This evaluation was conducted in the region of the Antarctic Peninsula, the hotspot of the continent where a warming trend was detected from 1950, with the increase of the mean annual air temperature in 3.54 degrees. The assessment of the topoclimatic factors influenced allow us to better understand the impact on the ground surface temperature and on the dynamic for the freezing and thawing season on Barton Peninsula. To achieve this objective, a set of 20 temperature mini loggers were installed on the peninsula, buried at 2 centimeters depth, and programmed to record temperatures every 3 hours. As a result, series of ground surface temperatures were obtained for the period between March 2019 and February 2020. These series were then used to calculate the ground temperature parameters as the mean annual ground surface temperature, the freezing and thawing degree days, the duration of the freezing and thawing seasons, the freeze and thaw cycles, and also the daily ground thermal regimes. These parameters and variables representative of the topoclimatic factors were then used in the multiple factorial analysis to evaluate the factors' influence on the ground surface temperature. The variables selected by the importance were then used in the discriminant analysis to model the patterns of daily ground temperature on the peninsula. Regarding the information on snow cover, SAR image from Sentinel-1 were used to estimate the snow cover duration on the peninsula. Moving to the results, the ground thermal regime is characterized by a freezing season with a duration of 7 months from April to November. And the mean annual ground surface temperature was between -2 degrees at 254 meters above sea level, and 0.6 degrees at 16 meters above sea level, with a strong correlation, was a negative correlation of 0.9 with the elevation factor, as you can see on the first chart. The freeze and thaw cycles that occur mainly in the season's transition varied from 25 to 91 cycles, being the higher frequencies associated with the sites where the period with the snow cover were shorter. And it has a correlation with the snow cover duration, as you can see on the second chart. The freezing degree days between 438 and 1041 have a strong positive correlation with the altitude, with a value of 0.9, and suggests that the intensity of the freezing seasons tends to increase with the altitude. The results obtained from the multiple factorial analysis demonstrate that the two dimensions explain 51% of the variance among the sensors when we consider the ground temperature parameters calculated. Moreover, the potential solar radiation, the snow cover duration, and the elevation were the most important variables to the dimension 1, while for the dimension 2, the most important variables were snow cover duration and the potential solar radiation. Through this method, it is also possible to analyze the relationship between the ground temperature parameters and the variables, represented by their position. Examples are the strong correlation between the elevation factor with the freezing degree days and with the mean annual ground surface temperature. In this case, with a negative correlation, this is seen on the opposite side of the chart. The snow cover duration and the duration of the freezing season also have a strong correlation. But for example, the freeze and thaw cycles and the duration of the thawing season had a negative correlation with the duration of the snow cover. The potential solar radiation also has a strong positive correlation with the freeze-thaw cycles and with the duration of the thawing season, and a negative correlation with the duration of the freezing season. The ground surface temperatures record were also analyzed in order to identify types of daily regimes. We identify 6 types present on the left on the slide. 2 regimes with unfrozen ground, 2 with the superficial freeze and thaw, and 2 with frozen ground. Then these types of daily regimes allow us to identify 4 patterns of annual successions of daily regimes. On the group A, the sensors have a high frequency of frozen regimes, which result in a long frost season. And they are characterized also by the different onset of the thaw season. Group B has a moderate frost season, followed by a high frequency of superficial freeze and thaw cycles in the season's transition. Group C and Group D also have a short frost season with a low frequency of frozen regimes. But in the case of the Group C, we have a high frequency of superficial freeze and thaw regimes in the season's transition, which indicates a slow warming of the ground. And on the case of the Group D, we have a low frequency of superficial freeze thaw regimes, which indicates a fast warming of the ground. Discriminant analysis allowed the specialization of the 4 patterns of daily ground temperature regimes with the variables identified in the multiple factorial analysis. Therefore, we use the elevation, the potential solar radiation, and the snow cover duration to estimate the zonation of the department. From this approach was observed that the regime with the long frost seasons with a blue color is present near the snow patches on the peninsula, where the snow cover stays for longer periods, while the moderate frost season with a darker green is present at sites above 160 meters above sea level. The difference between the warming velocities on the regimes with a short frost season are controlled by the altitude. Therefore, for the group C, we have a short frost season and a slow warming in sites above 50 meters above sea level, while the fast warming is present below the 50 meters above sea level. From the comparison within the regions associated with the pixels and the sensors, a slightly offset was identified in cases where the spatial resolution does not represent the microtopography. For example, here we have one sensor that has a regime of a pattern from the group A, but because it's a bit far away from this pixel, it's allocated to a pixel where we have a group C and not the group A. To conclude, the topoclimatic factors that have the most significant influence on the ground thermal regime are the elevation, the potential solar radiation, and the snow cover duration. We identified 6 daily ground thermal regimes in Barton Peninsula, 2 with unfrozen ground, 2 with superficial freeze and thaw, and 2 regimes with frozen ground. Onset of the thaw season marks the difference in the ground surface temperature regimes. And from our model, 6% of the sensors installation sites were correctly classified on the model. The model performance was conditioned by the resolution of the digital elevation model that has a resolution of 10 meters. And finally, I would like to acknowledge the institutions that supported the research activities on Barton Peninsula and also the development of my master thesis.
Awesome, thank you so much. While folks are looking for either the Q&A button or want to raise their hand, and I can allow you to speak if you want to ask your questions verbally, I might lead off with a question. Jenna, it seems like you've shown really nicely the importance of snow cover in controlling ground thermal state, but what did you find controls the distribution of snow cover? Is it just altitude or elevation, or are there other factors that control where the actual snow is so it can control ground thermal?
On Barton Peninsula, we have a strong influence of the wind. And what we saw, this was the snow cover during the thawing season, or for the spring and summer, the period of time where it's possible to map the wet snow, because in the winter it's not possible to do SAR image. And the snow patches are mostly present on the depressions. So they stay longer in the depressions or on the concavities of the surface. So by the influence of the wind, there is a redistribution of the snow that tends to be then on the depressions.
Very cool, thank you. I'm happy to open up the floor to a question or two from our attendees. You can either use the Q&A function or raise your hand. Well, if there aren't any additional questions for now, we can always circle back. We have a little bit of time at the end. It looks like it's me and Joanna this morning in terms of our speakers. So maybe I'll go on next, and then as questions get motivated, we can have a little more discussion at the end or end early. So thank you so much.
Thank you.
All right, let's see. I'll get my talk loaded up. There we go. So thank you all. Just to sort of carry on this theme of what are the controls of melt and thaw in Antarctic permafrost systems. I'd like to talk with you today about some efforts to determine the duration of active layer thaw and the growth of actual saturated wetlands in Antarctic permafrost over in the McMurdo Dry Valleys using satellite data. And this was some work done by me and as well as some colleagues at Northern Arizona University and some outstanding students. And basically, the important take-home message for this is that as we see thaw beginning to become a little bit more widespread in Antarctica, there's the real potential for wetted active layers to become biogeochemical reactors. And so understanding the timing and extent and feedbacks that govern where thaw is occurring seems extremely important. And we're going to use satellite imagery to try and figure this out. We're working in the McMurdo Dry Valleys over here in the Trans-Antarctic Mountains, and particularly looking across the Dry Valleys region. And what we're looking at in this study is water tracks. So these are these shallow subsurface meltwater channels that form when the soil thaws and become saturated. These are channelized groundwater conduits that form in the active layer. And so they are sort of wetted zones that wick up to the surface and darken. And we know these features are widespread. They are damp to actually saturated, and they tend to warm quite a bit more than the surrounding soils. And so this is a real recipe for biogeochemistry. What we know about the water tracks is that they thaw deeply. So typically 40 to 60 to 80 centimeters in places versus 20 to 40 centimeters in dry soils that don't have as much water in them. We have, let's see, I don't know if I can pause. Let's see. Gonzalo, did you have a question to jump in now, or let's see. Can you put any questions in the Q&A?
Sorry to interrupt, Joy, but Gonzalo was saying that he can't see the sharing presentation, although I can see. I'm not sure what the problem is. Yes.
Oh, okay, good. Very curious. I hope it's coming through. Otherwise, it'll be in the recording. Otherwise, I'm happy to share slides too. Great. So yeah, our water tracks are wet. Oftentimes reaching saturation at the base of the ice table or exceeding 10% soil moisture at the surface, again, versus about 1% soil moisture off tracks. And we know the water tracks are salty. They're full of solutes. Here's a plot with dissolved chloride content in the water tracks on the x-axis, and actually dissolved silica content in micromoles on the y-axis. And what you can see with these is our water tracks, and sort of the green and red dots here are some of the most solute concentrated active layer fluids in the McMurdo Dry Valleys. Certainly wetter, saltier, and more full of chemical weathering products like silica than streams or glacial melt or rivers. These soils are really sites of biogeochemical change. And what we don't know about them, and what seems to be really important, is trying to figure out where these wetted biogeochemical reactors are and what their change has been over time. You know, is thawing becoming earlier? Are the soils becoming wetter? Are they staying thawed longer? This might be a sign of some kind of biogeochemical feedback in the active layer. And so our goal here is to figure out when water tracks are thawed and wet. For the longest time, the way to do that has been looking for dark pixels in worldview imagery and sort of high resolution commercial satellite imagery. And if you see wetted soils here, they're dark toned, and you say, okay, these are wet. But this approach has been really strongly limited by the spatial, not so much by the spatial resolution, the spatial resolution is outstanding, but the temporal resolution. It's unusual to get more than a handful of worldview frames over any given part of Antarctica over the course of a season. And so in this project, what we started doing is using Planet Labs planet scope imagery. These are sort of daily almost image collections taken over the McMurdo Dry Valleys. And they give us this unprecedented time resolution to determine when darkening occurs in the soil, which we can infer is a sign of wetting of the soil and thaw of the active layer. And you might notice that these images look a little bit unusual as we're looking down on some water tracks growing here in the mouth of Taylor Valley. And that's because one problem we're trying to address in this study is the fact that when people have looked for darkened pixels as a signature of active layer thaw and wetting of the active layer, there's often darkening from shadowing or roughness. In previous studies, there's probably an over-exaggeration of where soils are wetted. And we certainly see a lot of rough features in the landscape. As anyone who's worked in Antarctica knows, there's plenty of shadowing and darkening from non-wetness sources. And so what we've done in this study is a terrain correction method, where we take the original color image, this red, green, blue color image that has a bunch of dark pixels in it. You know, we have darkness that could be resulting from topography. We have darkness that could be resulting from soil moisture. And we correct it using a method developed by Mark Salvatore and applied by Lily Simonson on this team to remove shadowing and changes in brightness due to topography. So we take a hillshade using the 2014 LiDAR in this region and make that hillshade using the time of collection data for where the sun is in the sky for the satellite image we're looking at. And we then plunk down a series of training areas inside each of these images, which are zones that have a variety of topographical expressions, so north, south, east, and west, but that don't have albedo differences due to, for example, snow on the ground or water track wetting. Sometimes it can be kind of hard to find those spots. And then we sample pixel by pixel on the hillshade, which is just illuminated by solar conditions, and the color image, which we've summed up into sort of a single channel panchromatic data set. And when we do that, what we find is there's a very strong correlation between the predicted brightness of the surface, that's the hillshade DNs here on the x-axis, and the actual brightness of the image, which is the summed DN values in the satellite image on the y-axis. And so we can see as you get brighter in the hillshade, because you're an illuminated surface, your image tends to get brighter. And so what we actually do is then subtract out the brightness in the image that's a result of diffuse illumination. And then we determine the correlation between the hillshade brightness and the satellite image brightness, and then subtract that out from our image. And so any offset from this line, from this best fit between the hillshade brightness and the satellite image brightness, is a result of intrinsic differences in surface brightness. So this is not then brightening and darkening because of shadowing or roughness. It's brightening and darkening because the material of the surface actually has a different albedo. And primarily that difference is going to be from either snow presence on the ground. So here's our color image on the left and our terrain corrected panchromatic image on the right. And of course, snow pops out because it has an intrinsically higher albedo than the surrounding soils. But all of our water tracks here, these wetted soils, either in a stream channel over here or in our water tracks here in the channel, are dark because they are in fact darker than the surrounding soils. And so in this case, our dark pixels are actually dark pixels, and these are likely our wetted and thawed soils. So we can take this terrain correction method and go through our huge catalog of planet data and determine where we have water tracks that are confirmed. So the terrain correction process has been run through, and we see linear dark patterns associated with active layer thaw. We have unconfirmed water tracks where we see dark pixels in the same spots, but for whatever reason, the image could not be corrected. There's no clear correlation between the time of collection hillshade and the satellite imagery. It could be noise in the data or other factors. And then no water tracks. So we can correct the image and say, okay, convincingly, there are no dark pixels in here associated with water track flow. And so now what we've done is applied this across 10 sites in the McMurdo dry valleys, from the warm coastal regions over here in the east up to the highest, driest, coldest sections of the dry valleys over in the west. And what we have is an absolutely unprecedented record of water track growth and active layer thaw. So here we are in the Guglielmin Glacier Basin in central Taylor Valley, looking at a series of images, really, so you can sort of see any day that it's clear. We have a planet scope image of the surface, and you can see growth of the water tracks down the valley wall, sort of day-to-day variations in where the active layer is thawed and wet, growth of these small ephemeral water tracks around the main channel. And when we look at this graphically, we see something rather striking. So here's a plot that shows days since November 1st, 2018, when this data was collected. So we're starting here at November 1st and going across the Antarctic melt season. We have temperature on the red, green, and blue colored lines. So red is surface temperature at 0 centimeters, green is temperature at 5 centimeters, and then blue at 10 centimeters. This is from the nearby Lake Hoare weather station from the McMurdo Dry Valley's long-term ecological research team. And then all of these vertical lines are planet scope images. So, this would be typically like a decade's worth of worldview imagery. Here we have it as daily observations. And pink images are unconfirmed water track activity. Purple lines are confirmed water track activity, and black lines are no water track activity, and that's confirmed. And the thing that's striking about this is we really don't see the beginning of water track activity in these pink lines until subsurface temperatures reach thawing. And so this is really confirming at this site that the ground ice is a key water source for these darkening water tracks. This is ground ice thaw and active layer formation. What's striking about this is that we actually see darkening late into the melt season. So all of those solutes that are present in the water tracks are either depressing freezing points quite a bit, or potentially rehydrating as vapor phase kind of products late in the season. And this is extending the hydro period, the wetted duration of the active layer, potentially into February and even into March. These are long-lived meltwater features in some form or other. And so across all of our sites, what we've seen is that we previously thought that water tracks really began in December and were done by the end of January. But across all of our sites, what we see is our confirmed activity is easily pushing into November based on the high resolution planet data, well past the end of our typical field seasons going into February, and potentially with unconfirmed activity even into March. And so what we're seeing with these remote sensing studies is that these water tracks and wetlands are really complicated, and they're dampening and darkening earlier than we thought, potentially in early November. They're staying damp and dark much later than we thought. Which gives us much longer periods of time for active biogeochemistry, for organisms to grow, and for water to exchange with the subsurface. So I'm really excited about getting back into the field, hopefully soon. But until that happens, we can use these remote sensing data to really change our understanding of when and where Antarctic permafrost is thawing and active layers are growing. And so I'll end with that, and would love to take any questions or have some discussion either about my presentation, or about Joanna's as well, because I think it's just us here. So it's good to see some friendly permafrost faces, and let's have a chat. Be happy to turn on your cameras or turn on your microphone, and we can talk about what's going on. Gonzalo, if there's any issues with getting the slides, I can beam them to you. I'd be happy to do that. So yes, so SAR is the next step. I think that I'm really excited about getting into SAR imaging for detecting water tracks. There's this classic sort of resolution mismatch that these are very, very, very small features. But obviously the new Sentinel SAR data is pretty darn high spatial resolution. So I think that's the next step. And it was cool to see, Joanna, I mean, if you'd like to chime back in again, about your experience working with the SAR data and its any relations with either soil moisture, or talking a little bit more about your sort of wetted snow detections, that would be great too. What's the way to get into that?
Well, I saw that, for example, on Barton Peninsula, we tried to manage one day on the field where was synchronized with the satellite. So when we have one image, the collection of one image, we were on the field collecting data about the snow patches, the temperature, the grain size, this type of parameters. And then later I collect the SAR image, and I start with the process of the image in the snap from ESA. And I saw that we have some troubles with the terrain. For example, one side of the peninsula has a steep slope, and the shadow from this slope resulted in lower values on the image that were confused by, like, for example, it was wet snow, and in fact was all just the shadow from the slope. I had this type of problems, and the thing is, since we know the peninsula, we managed to identify these problems on the image, and we know that, for example, this type of slope, because it's very I'm forgetting the word, but because the slope is very high, this is not a snow patch, but this is the shadow from the image. And well, this was the problem. And then to map the snow, the wet snow, in days, for example, where the temperature decreased a lot, we have on the top of the snow patch, the ice gets drier. So for example, we can see the snow patches increasing when the melt of the water starts, and then, for example, they decrease again because of this. And well, what's my experience treating the SAR image? But they are very useful for my work to map the presence of the snow patches, since they influence a lot on the ground surface temperature and also on the permafrost. And as I told you on my presentation, I'm starting my PhD now, and I will working with the modeling of the permafrost thermal state. And the snow, it's very important for that. So I will use the SAR image again, and I have to improve the method, because it's very important for my approach.
Awesome. And thank you, Gonzalo, in the chat for the information about the other sensors. Yeah, this is, I think I think what Jenna was saying, and what I think I hear from a lot of people, is that moving into non-optical wavelengths for the kind of soil moisture analyses and snow presence work that we all want to do is the way to go. Hopefully this field season I'll be flying an L-band radiometer from a drone for actual soil moisture measurement. And so kind of combining SAR with L-band is going to give us I think a better view of what's going on in the shallow subsurface. And so, yeah, it's great to see that that's available now, and it would be nice to talk offline or at some other time to kind of coordinate what some of these observations might look like, because obviously we're seeing a lot from the ground, from the air, and then from satellites. So this is, we're entering a new era from I think what we've seen in the past. Any other comments, questions, discussions, or is it time to grab an espresso or run to another session? Well, seeing it's quite crowd, I would say it's been wonderful hearing a couple of talks this morning. It's been really interesting, and yeah, hope to see you all in the field or at other conferences in the future. Certainly, if folks have any questions, feel free to email me or get in touch, or we can download the videos too. This should be online pretty soon. And this was fun. I'll see you all in the future.